took the blast in Tunguska. This was that big meteor that exploded in Siberia in 1908, and scaled it up to fit Manson so we can get a feeling for what some of the effects would be. This was an air burst. It didn't actually hit the ground, but many of the effects were the same, so you can kind of use it as a scale effectively. One of the things it did is blow a lot of trees over, away from the impact area. You see the arrows point to the directions that the trees were leaning, so that blew a bunch of things over. And from that, they were able to estimate that this had a energy release somewhere between 10 and 40,000 kilotons. So somewhere in the same range as the atomic bombs that were dropped on Japan, maybe a little more. Now, if we scale that up to Manson, there's the Manson crater on the U.S. We have 5.5 billion kilotons, so it's somewhere 200 to 500,000 times larger than the Tunguska one. So scaling up isn't exactly correct, but it'll give you a ballpark. So what would happen if we had that impact today? First thing, the electromagnetic pulse that went out would immediately set everything inside this yellow circle on fire. So all trees or anything that was there would be set on fire immediately. We talked about the trees that were blown over as we moved away from Tunguska. Manson would have blown trees over as far as Chicago and St. Louis. Then there was a trader who was riding his horse through this forest of Siberia and was knocked off his horse unconscious by the shock wave from that impact. So if we scale that up, we have people being knocked unconscious as far away as Pittsburgh, Atlanta, Albuquerque, Salt Lake City. So I figured that unconscious, and you don't have to be a lot closer to be killed, so it's kind of split the difference there. And this would be a kind of a killing zone. So basically, most of the people between Columbus, Ohio and Denver, Colorado would be killed by that blast if it happened today. So it would be pretty catastrophic. Here's a little aerial photo. I don't know how many of you recognize it, but you are here. If we blow that up a little bit, zoom away a little bit, and we sit the Manson going down on top of it, that gives you a feeling for how big the impactor was compared to the town of Cedar Falls. Pretty good size. But of course, it's not just going to rest on the ground. It's going to hit and release a lot of energy. And it basically would have vaporized everything inside of this circle. So that took care of the whole UNI campus and a lot of the rest of town. If we zoom out a little bit, there's the meteorite right there. Here's the vaporized zone. Everything inside of this zone would have been melted and thrown out of the crater as molten rock. Everything inside this zone would be blasted into sand to boulder-sized pieces and thrown out as ejecta. And then inside this circle is where the ground would have been lifted up and then collapsed down inside of that as a rubble zone, the down-drop block around the outside. So that gives you a crater sitting here in Waterloo, just about like that. Pretty big thing. Glad it doesn't happen very often. Well, if it happened again in Manson, what would it do? This is an interesting website here. It's called the Impact Effects Calculator. You can basically punch in all the parameters of your impact, how big a meteorite you have, how fast it's going, what angle it's coming in, what it's made of, what it's smashing into, and all those things, and see what the effect would be at some distance away. So I plugged in 101 miles between Manson and Cedar Falls to see what would happen here if it hit there again. So first thing that would happen is we get this maximum radiation, this electromagnetic pulse would hit here 1.7 seconds after impact. There'd be a fireball in the sky that you'd look up and see that would be equivalent of about 38 times the size of the sun in that direction. You see this big flash. The radiation would hit you, or the radiation would last for 6 minutes, and it would have the intensity of 137 times the heat of the sun. So it wouldn't be good. Ignite everything here right away. Seismic effects, effectively we would feel an 8.5 magnitude earthquake from that, and it would arrive 32 seconds after the impact. Some other things, the air blast, that's pretty important. That's the actual shock wave through the air that will hit you. It would take 8.2 minutes to get here, and when it arrived it would be 28.8 pounds per square inch. Well, what does that mean? Here's a little chart that shows you that anything above 12 pounds per square inch is 98% fatalities. So that shock wave is going to kill everybody that wasn't killed by the electromagnetic pulse or the earthquake. Maximum wind velocity from that, 647 miles an hour. Yeah, and you can see it would do a real number on any of the buildings. So Cedar Falls would be pretty well totaled by this. This wasn't the impact that killed off all the dinosaurs. The actual dinosaur impact was down here at Chicxulub, the Yucatan Peninsula. So I just want to take a quick look at the energies involved in that, just to give you a feeling of what's involved in these impacts. There was a book on the Cretaceous Tertiary boundary called Night Comes to the Cretaceous. And in there, they estimated that the energy from Chicxulub was about 100 billion megatons. So what is 100 billion megatons? If we exploded one Hiroshima-sized atomic bomb, that's 15 kilotons for every living person on Earth, all 7 billion of us, that'd still leave us about 400 million bombs short. So wow, that's a lot of energy. And I found another example that is pretty interesting too. It'd be equivalent to exploding a 1 megaton nuclear bomb for every 6 kilometers on Earth. So let's take a look at Black Hawk County here. Here's 1 megaton bomb every 6 kilometers, so that wouldn't be good either. You think about that, extrapolate that over the whole Earth, you get a feeling for the incredible amount of energy that these kind of impacts impart. When is this going to happen again? Well, Gene Shoemaker, again, and his wife had been studying near-Earth asteroids. Those are the asteroids that are kicked out of the asteroid belt and crossed the orbit of the Earth, like the ones that Siberia did not too long ago, to try to estimate how often these things impact. And what they came up with was that we get a Manson-sized impact about every 1.2 million years on Earth, and on land about every 3.4 million years. The big Chicxulub ones, the ones that really do the damage, once every 100 million years or so. So that's real good. That doesn't happen very often. So that's the Manson impact. One other thing I was going to tell you about, if you pay attention to your U-Haul truck art, you'll see that Iowa is now represented by the Manson impact structure. And this is what that map looks like. It's kind of a picture of the explosion going on at Manson. You can see some meteorites zooming in. Here's my cross section with corn drawn to scale. This is a 7 mile tall corn. And then they wanted a formula for this thing. So I gave them this formula, which is a formula for the ballistic distance that material is thrown out of the crater. How far does it fly, based on the amount of energy and the angle of ejection and all that kind of stuff. So when you see this going down the road now, you can explain it to people. Okay, one other impact structure I want